Okay, welcome back, guys. We are going to be on page 219. Okay, and we're going to talk about the normal distribution today. So it's a bit of a long lesson, but we'll get through it. So, the shape of normally distributed data. So we're going to look at some examples here. We're going to look at what the definition of normal distribution is, and then of course we're going to do some examples. So, it's been discovered that many observations of physical measurements, such as length, volume, mass, time, etc., all have common characteristics of how their data is distributed. Okay, so how their data is distributed. The examples below show histograms developed from data with these common characteristics. Okay, so weight of infants, time taken to complete an assignment, height of students, and marks. Grades can be graphed this way too. So it says draw a frequency polygon by connecting all the midpoints at the top of each bar with a smooth curve. Okay, so basically we would just kind of go like that's our smooth curve. Okay, that would be our smooth curve. And then this one's kind of, just have to be careful and get the general gist of it. There we go. Okay, so the big idea to see here, those are all, we would call that a bell shape. Okay, and thusly they are called bell curves. Okay. All right, so normal distribution itself. So data which results in a frequency polygon with a bell-shaped curve is said to be normally distributed. Okay, so bell-shaped curve, normal distribution. So the curve itself is called a normal distribution curve, or the normal curve, or the bell curve, and it is widely used to make predictions in statistics. Okay, and so this, you would definitely need to know the general normal distribution curve. Normal distribution curve. So frequency is on the, that would be our y-axis, which remember, that's our range. And then the data values are on our x-axis, and that would have to do with domain. Okay, and I'm just going to focus this a little bit. Every time I move it, it changes. I don't know if that even helped. Okay, but that's anything that we are going to be looking at will follow this bell shape. Some will be super close to it, like these ones right here. This was the closest one because it had more data points. This one was the least like because it had a least number of data points. Okay, so understanding the normal distribution curve by investigation. So we're going to look at some examples, investigate this curve. So a normal distribution curve can be best understood by an actual example, such as this one here. So a manufacturer who makes 100-watt light bulbs for Globe Bright Incorporated is interested in determining the distribution of the lifetimes of the bulbs. Okay, so distribution of the lifetimes of the bulbs. After testing 44 of the bulbs, he calculates the mean life, so remember mean means average, of the bulbs to be approximately 900 hours, and then the standard deviation, okay, that's our sigma, mean is mu, to be approximately 50 hours. So the lifetimes in hours of the 44 bulbs tested are shown. So here's all the data that this guy collected. Okay, and then here's just the information summarized up. Okay, remember mu means mean and sigma means the standard deviation. So mu mean, sigma standard deviation. Okay, so verify the histogram to the data. All right, so basically that's just us saying, yes, this matches this data here. Okay, so we're just going to trust that that's the same there. Okay, and then use the histogram to complete the following table. Okay, I'd like to get a little bit closer, but I don't want this thing's being really finicky. Okay, so the number of bulbs, so this means less than 800. So here's 800. Less than 800 would be right here, and if we trace this over, okay, if this is 5, that means each one of those is 1. So therefore that's 1. Okay, from 800 to 850, we would look up here, that'd be 6. From 850 to 900, that's 15, and so is the next one. Okay, and then we come back down to 6, and finally back down to 1. Okay, so if we were to take the sum, okay, so remember that's our symbol for sum. So if we were to add all of these up, okay, it would equal 44. Okay, so all those added up equal 44. So then the bottom part here, so they give us a little sample here, we're obviously taking this number and dividing it by that sum. Okay, so 1 over 44, 6 over 44, 15 over 44, which we see here is 34.09%. Back to 6 over 44, and 1 over 44. Okay. So if we were to plug this into our calculators, I'm just going to use a different color pen because it's kind of not showing up. I like using pencil, but so if we were to actually calculate this, put this into our calculator, we would get 2.27%. This would be 13.64%. Okay, and we already did that, and so of course this is going to be a repeat because it is symmetrical. Symmetrical means the same on both sides. Okay, and then we've got those values right there. Okay, so what this means is that 34.09% of the lifetime of the bulbs is between 900 and 950, and 34 point whatever percent, same thing here. So if I were to just say, where's the majority? Okay, so the majority of my light bulb hours, specifically, if I were to add these together, so let's say 68%, 68% of the time, the lifetime of my light bulbs is between 850 and 950 hours. Okay, so that's what doing this type of statistics allows me to predict. Okay, so now let's look at on page 221 here. We've got a question. So it says, using the mean is 900, or mu is 900, sigma is 50, write the following numbers in terms of mu and sigma. And then we should actually say and/or. Okay, so if I had 950, okay, well obviously I'm adding these two together. Okay, because 900 plus 50. 850, okay, well now I'm subtracting. All right. 800 itself, there's nothing I can really do here. I could start with just mu, so my average, minus 20, for example. And then 1050, so then I would start with, where am I here? Oh, yeah, mu, okay. And then 1050, well, that's going to be sigma plus sigma plus sigma, because that equals 150. So then if I've got 3 sigmas, I could write it like that. Mu plus 3 sigma. Okay, so we're doing this for a reason, you'll see down here. So complete the normal distribution curve based on the results for this example. Okay, well, this was 34.09. Either side of the 34.09 were 13.64. Okay, and then one more is 2.27. There we go. All right. So the data values we can also fill in. So that's the 900, 950. So this would be 850, 800, 750, and then up to 1,000, and then 1,050. Okay. So now number of standard deviations from the mean. Okay. So the mean is actually going to be this middle bar right here. Okay. So then if this is 1, that means this is 0. Okay? So 1, 2, 3 standard deviations from the mean. And then if I go this way, same thing except for negative. Okay? The next step, the data value in terms of mu and sigma. So they've got this one here. So we already stated this is the mean. So that middle bar in between the 34%, that's mu. So then that's mu plus sigma. Well, then this must be mu minus sigma. Okay? Here's 2 standard deviations. So remember, that's a standard deviation. So then if it's 2 standard deviations, I'd write mu plus 2 sigma. Okay? And then same thing here, except for now 3 sigma. And then of course if I go this way, same idea, except for subtracting. I'm kind of squished here, but that's okay. Okay? So I would definitely maybe star this. P.S. If you ever take any statistics classes in university or college, you will definitely revisit this. Okay, so if that's in your cards, definitely worth, really getting to know that bell curve. Okay, so the curve above is based on one particular example and is a good approximation for the standard normal distribution curve that we're going to see on the next page. Okay, so the standard normal distribution curve. And I'm just going to move that over and make sure that it's focused. So, for population data with mean of mu and standard deviation of sigma, oopsies, the normal curve is denoted by a capital N. Okay, and then we've got it listed like coordinate points, mu, and then sigma squared. So there's going to be a different probability distribution for every different value of mu and sigma. In order to compare normal curves and to solve probability problems involving normal distributions, we're going to convert normal distribution curves given in a problem into a normal distribution. Okay, so probability and other statistics, that's kind of the theme. And then what we're actually going to do is we convert basically the information we're given into the standard normal distribution curve, where it's, in the middle is the mean, then 34%, and then the 13-ish%, and then the 2%-ish. Okay? So the distribution represented by the standard normal distribution curve has a mean value of 0 and a standard deviation of 1, okay, which is then denoted by capital N, 0, 1. The equation of a standard normal distribution curve is this bad boy here. Okay, so we're going to put that around it. So this is read as the function of fx. So f of x is equal to 1 over the square root of 2 pi times e to the power of negative 1/2 x squared. So this is definitely something that we don't really go into. I don't even know if we use this right away. We will be talking more about what this is, but for now we can kind of table it. Okay. So if you were, actually sorry, I just realized that we've got this instruction. So if you put this into your graphing calculator, okay, you would get the standard deviation. For now though, just because I'm not there, there's E is a special button on your graphing calculator. I can show you. It's this one right here. Okay, but for now, you just go ahead and trust me that if you were to put this into your graphing calculator, you would get this shape. Okay, so you can go ahead and try that later, but for now, just also because we're, this is a long lesson. Okay, so the terminology of capital N is mu and then sigma squared, and the equation are not required for this course. So that's why I'm, kind of hesitant. They're just giving you, this is just that extra information of that's where it's coming from. There is it's based on mathematical expressions and equations, but for now we just need to know this bad boy. Okay? So the diagram shows the approximate area under the standard deviation, or sorry, standard normal distribution curve, and it's subdivided into the regions, each of equal width. So these are all 1 right there, okay? And then the percentage is included underneath. And so notice we didn't talk about the -1, so that's 0.13%, okay? So given this right here, the mean of the data, okay, well here's the mean, it's equal to 0. The standard deviation, okay, that's going to be 1 each time, okay? So blank of the data is above the mean, okay? So above the mean is all of this. So if I add 34.13 plus, actually, why don't we just do that right now? 34.13 plus 13.59 plus 2.15 plus 0.13, that equals 50%, which that makes sense, right? We would have 50% on this side, and then we would have 50% on that side to represent 100% of the data, okay? All right, so what percentage of the data is within 1 standard deviation of the mean? Okay, well that 1 standard deviation could be this way, or it could be this way. So then we would say 34 plus 34, so that's going to be 68.26% of the data. Okay, how much within 2 standard deviations? Okay, well we're going to start with that 68.26, and then we're going to add another 13.59%. So essentially for this number 5, we are adding this, 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 and this up, and it equals 95.44. So you could put that into your calculator, or you could just trust me. Okay, now it's within 3 standard deviations. Okay, so between the 2 red arrows, so I would add all of this up. Okay, so essentially it's 100%, subtract those 2. Okay, so that's going to be 99.74%. All right. Now the next 2. So how much, or what is the percentage of data between 1 and 2 standard deviations of the mean? Above the mean, sorry. Between above the mean. So then that's just this. This is between 1 and 2. It froze. Okay, this is between 1 or 2, and it's above the mean. So that's 13.59. Now the only difference between these 2, this one's below. Okay, well now we're talking about this one. However, it's still 13.59%. Okay, so that's just looking into the, oh, fell asleep. Wake up, computer. There we go. That's just using the standard deviation and trying to understand what's what. Okay, let's talk about the basic properties of the standard normal distribution curve. So the total area under is 1, and in terms of percent, this is representing 100%. Okay, the normal curve is going to extend infinitely to the left and to the right. Okay, so it's just going to keep getting smaller and smaller and smaller and smaller. The normal curve is symmetrical, okay, about the mean. So the mean is that middle part, and it just means that this side will look exactly like this side. Okay, so 50% will be on this side, 50% will be on this side to add up to that total 100. Okay, all of the data is represented by the area under the curve. So anything that you were to graph, etc., in a histogram, all that data is represented under here. And the area itself. So technically, we could calculate that area, and that would help us understand something about data. And then the mean, median, and mode are the same value. Okay, so we're not used to that being true, but we're going to look at some examples of this. Okay. Okay, so let's look at our first example. A nurse records the number of hours an infant sleeps during the day. Okay, and we see that here. number of hours slept. So we've got 10, 12, 14, and then C, D, A, B. He then records the data on a normal distribution curve, shown below. The values shown on the horizontal axis differ by 1 standard deviation. Okay, so that's important information, and it's pretty much always going to be that way, but anyway. Okay, so what is the mean of the data? Okay, well, we know, we've talked about this, the mean of the data is right in the middle, so that means the mean of the data is 12. Okay? What is the standard deviation? So that means, okay, this right here, that's sigma, okay, is equal to 2. All right? And then what are the values of A, B, C, and D? Okay, well, if there's the differences of 2, that means going back, that's going to be 8, that's going to be 6. So 6, 8, and then 16, 18. All right. What is the percentage of days to the nearest hundredth that the infant sleeps? Okay, so percentages. So between 12 and 14, okay, so you can't really see these lines, so I'm just going to color them in. Okay, it's going to be the same, so it's going to match up to be this one. So this is going to be 34.13. 34.13. This is going to be 13.59, 13.59, 2.15, 2.15. So we use, even though it's a different example, we're still using the approximate area of the standard normal deviation. So then between 12 and 14, that's going to be the 34.13%. Between 8 and 16, okay, 8 is here, 16 is here, so we would add up this, 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 and this to get between 8 and 16. Okay, and so then we calculated that in that one question, 95.44, and now less than 6 hours, so 6 was right here, less than 6 hours, so anything less than that, okay, on this side, that's equal, right, because it's symmetrical, 0.13%. 0.13%, so less than a percent. Okay, so why is it not possible at this time? We are going to learn how to do this, but what we've done so far, why is it not possible at this time to determine the percentage of days that the infant sleeps for less than 13 hours? So 13 hours would be right there, okay? So we don't know right now what it means for increments of less than 1 standard deviation. So we don't know the area under the curve for increments. So an increment is like an amount, okay? Increments of less than 1 standard deviation. Okay, for now, we will, but okay. Now, if we're going to be able to do this, we need to look at something called z-scores, which is the next section. So I'll give you a second still. We don't know the area under the curve for increments of less than 1 standard deviation is SD. Okay, I guess I could have put 1 sigma too, right? Okay. Z-scores. All right. So it's not possible with the given curve in that example to determine the percentage of days the infant sleeps for less than 13 hours because the model of the curve is limited to integer values of the standard deviation. So integer values mean like we only do 1 standard deviation, 2 standard deviations, 3. We don't do half. So, or we didn't. That's where z-score comes in. So z-score for a particular data value is the number of standard deviations the data value is above or below the mean. Okay? So, calculating and displaying z-scores on the normal curve. So we're going to consider that example still with the mean value of 12 and a standard deviation of 2. So we're still going to be referencing this right here. Okay? So the data value of 18 is how many standard deviations above the mean. Okay, this is going to be annoying. Oh, it's got us right here. We don't need to flip back and forth. Okay, so 18 is 1, 2, 3 standard deviations above the mean. So therefore it has a z-score of 3, because up here it says the z-score is the number of standard deviations. Okay, so it's equal. Okay, if I go 8, 1, 2, okay, well that's 2 standard deviations, which is a z-score of 2. The data value of 12 has a standard deviation, well, it's 0, right, because it's the mean. So that's going to be 0, 0. So then if we're talking 13, okay, well 13 is halfway between these two, right? So that means that it's half a standard deviation and it happens to be above the mean, right? 11 would be below. And so if it has a standard deviation of half, well then the z-score is half. Okay? So then we're going to fill this out right here. So we are going to talk about that. So this right here is mu. So now this is in terms of mu and sigma, so standard deviations. So 10 is mu minus sigma. 14 would be mu plus sigma. Okay. This would be mu minus twice sigma, because that's 2 standard deviations. 16 would be plus 2 standard deviations. And then 6 will be minus 3, which means 18 will be plus 3. So then the actual z-score, so remember, the z-score is equal to the standard deviation. So that means the z-score here, 0, minus 1, minus 2, minus 3, makes this 1, 2, 3, and then our R13, okay? So the next part here, how can the z-score for a data value of 13 be determined? Okay, you would just calculate the z-score for the data value and then list the data value and the z-score on the curve. Okay, so this is going to be positive 5. So then we would say the z-score for 13 is equal to 0.5. All right. So then we are going to be doing something with this. Hopefully that makes sense though. So here's the formula. A z-score for a data value can be calculated using this formula. So there's my z-score. X is the particular data value. So in this case, that would be like the 13. Mu, that of course is the mean. There's my standard deviation. Okay? So a z-score indicates the number of standard deviations that a data value lies from the mean. So it's with respect to the mean. A positive z-score means that it lies above the mean, which that makes sense, and then negative is below the mean. Okay? And I'm just going to highlight this right here. And then just make sure you know how those match up. Okay. So then, looking at our standard bell curve, okay, oops, right here. Okay, so this is, we talked about this before. This is nothing new. We said that 68% is within 1 standard deviation. So within, that means either side. 95% is within 2 standard deviations of the mean. And then 99.7 is within 3 standard deviations of the mean. Okay? All right. So then this is just using that to fill this out. So approximately 68% of the data lies between, blurry again, there we go, between Z and Z. So that would be in between negative Z and positive Z. Okay. And then 95%, okay, well that's this one here, 2 sigma, so remember that my standard deviation is equal to my z-score. So that's going to be between plus and minus 2. And then that 99.7% is going to be between plus or minus 3. All right? Okay, so that's the gist of it. Definitely know this. This will actually help you. So if you can write out, like sketch the graph, sketch this, which it's easy, right, because it's symmetrical, same thing with here. Then, like for any quizzes and tests, if you write that down first, right, then you can like always revisit it and you don't have to draw it each time or anything like that. Okay? Okay, so all we have left now are some class examples. So we've got another basketball team. Oh, it's the same basketball. Oh, no, it's not. It's different because there was a mode there. Anyway, or I think, it doesn't matter. Here's the basketball team. If the mean height is 190 and the standard deviation is 15 centimeters, calculate the z-score. Okay, no problem. So this first part is done for us. So x minus mu, oh, my classroom light's turned off. Actually, it's not bad though. Okay, 170 minus 190. So here's this first one. Okay, so 170 minus 190. Oh, and the lights are back on. So mu is my height, or sorry, the mean height, and then sigma is that 15. So we get that the z-score for 170 is negative 1.33. Okay, so this is for the shortest player. Sorry, I think I got distracted by the lights. I didn't say that. Shortest player is shown. We're supposed to do it for the tallest player. So this is our template. We're going to do exactly the same thing. Okay, our tallest player is 212. So then we just go 212 minus that 190 over 15. So see how those are exactly the same. The only thing that changed was the specific data value. So then when you actually plug this into your calculator, so 212 minus 190 divided by 15, you should get 1.47. Okay? So that's the answer to class example 3. Okay, so if it ever asks you to calculate the z-score, you use this formula and you just plug in the information given to you. And maybe, like, this is a pretty easy question because it gave us the everything, but you know how to calculate the mean height and the standard deviation because we learned that last day in our lesson. We can do that in our calculator. So don't be surprised if you just get data and then you're asked the z-score, so then you will have to calculate the mean and calculate the standard deviation first. But you know how to do that, so no big deal. Okay, class example 4. So z-scores can be used to compare data from different normal distributions by converting the distributions to standard normal distribution. So, oh, my computer keeps falling asleep, lights are going out. Why you do this to me, technology? Okay, we're back. Different standard. Okay, so we're giving an example, but we're going to compare it to our friendly bell curve here so that we can answer some questions. Okay, so Tony's midterm marks are shown below, together with the class mean and standard deviation for each subject. By calculating z-scores, determine in which subject Tony performed best relative to the rest of the class. Okay, so here's Tony's marks. Here's the class average. Here's the standard deviation. Okay, so once again, here's our formula. So z is equal to x minus mu divided by sigma. So essentially, we want to calculate the z-score for math, for chemistry, and for physics. Okay, so let's just use little subscripts. So this will be the z-score for math. Okay, so then my x itself, that's going to be Tony's marks. Oopsies, 74. Yep. My mean is my mu. Okay, so minus 68. Oh no, my pen's running out. Blue. 74 minus 68. And then my standard deviation is right there. So that's going to be divided by 12. So all we do is take our information, substitute it in for the different values. And so it's very important. You need to know in this table, or however the data is given to you, what's going to be each one of these variables. And then it's just you plug it into your calculator, okay, and you will get, so for this example, 0.50. Okay, so that is the z-score for math. So then we would go ahead and we would do the z-score for chemistry and physics as well. So we're still using the exact same formula. We're just plugging it in. Okay, so for chemistry, now it's going to be 79 minus 73 over 14, and 68 minus 66 over 11. So see how all of those match each one. So my physics, I used these numbers. Chemistry, I used these numbers. So then we do the math, and when you plug it in, you should get that the z-score for chemistry is 0.54, and the z-score for physics is 0.18. Okay? So then which one of these, to answer the question, did he perform the best with respect to the class? Okay? So then for this question, you might ask yourself, okay, is it the highest? Is it the lowest? It's going to be the highest one. So his z-score is highest in math. Okay, so Tony performed best in math because his z-score was the highest. So best in math because, B/C is because z-score is the highest. Okay, so that means he was that much further away from the mean, which is the average. Okay, let's look at another class example. So once again, some class marks. So the average mark on an English exam was 63%, and the standard deviation was 12. If the marks were normally distributed, and a student's z-score was 1.5, well then what was the student's actual mark? So we are still going to use this formula, because if you look at this, so if the average mark was 63%, okay, well that's our mu. Okay, standard deviation is sigma, and then we've got a z-score of 1.5. So that means that we're trying to solve for x. Okay, so now you can plug this all in and rearrange, or you could rearrange first. Okay, we'll just plug it in. Okay, and go back to, okay, so 1.5 is his z-score. X is what we're trying to find. Mu is the 63% of the class, and then the standard deviation of the class is 12. Okay? So we want to isolate x. So the first thing we're going to have to do is cross multiply that 12. So that's 12 times 1.5 is 18. So then I've got this. So then all we have to do, so here to here, we multiplied by 12. And then our next step, we're going to add 63 to both sides. So then that's going to give us 81 is equal to x. So that means the student got 81%. Good for him or her. All right? So just a different way to use that formula. Okay? And you could essentially, now that we've learned this formula, as long as you have 3 pieces of information, you can solve for any of the fourth one. Okay? Just like for sine law or anything else we've done. Okay, 2 more examples. And then we're done. So the weights of a large shipment of cantaloupes, all right, are normally distributed with a mean of 2.3 kilograms. Okay, so mean is 2.3. The weight of a particular cantaloupe is 1.7. So since this is talking about a particular piece of data, okay, that's going to represent our x in our formula. Okay? And then it says, which is 1.01 standard deviations below the mean weight. Okay, so sigma is equal to 1.01, but the important part in there, below the mean weight, so that means we're going to have a standard deviation of negative 1.01. Okay? And then determine this, oh crud. Okay, so which is that many standard deviations? Sorry, this is z. This is our z score. Okay, because remember our z score is equal to the standard deviation. So what we're looking for, determine the standard deviation to the nearest hundredth. Okay? Okay, so we're going to start off with our formula. Z is equal to x minus mu over sigma. And then this is what we're looking for. So we're going to isolate it. So I would, right here, remember, if what we're looking for is on the bottom, these two switch places. So x minus mu over z. Okay? So now it's just nicely rearranged. All we have to do is substitute in. So my x is 1.7, my mu is 2.3, and then z is negative 1.01. So 1.7 minus 2.3 is negative 0.06, or 0.6. And then you would just divide, and so since we've got a negative divided by a negative, we're going to end up with a positive. So then my standard deviation is 0.59 once you put that into your calculator. Okay? Alright, anytime I think of cantaloupes, I think of that joke, the why were the two melons sad? Because they cantaloupe. I'm tired. Okay, so class example 7. Last one, we can do it. The marks on a math exam at a university were found to have a mean of 52, okay, there's our mu, and a standard deviation of 12. Okay, there's our sigma. A professor who thought the exam was too difficult decided to adjust the original marks by raising the mean to 65. Okay, so this is our new mu. While reducing the standard deviation to sigma, so this is our new sigma, and leaving the z-scores unchanged. Okay, so what would the new mark be for a student who received an original mark of 34? So side note, before we get into this, this is called marking on the curve. Okay, and it's specifically called the curve, obviously, because of the bell curve. So this is something that some universities do. You know, it happens. Anyway, so this information that we're going to use, we still want our formula. There we go. Okay. So my original mark of 34, hopefully you're realizing that that is going to be x. Okay? And then my mu, so my original average was 52. So we'll do this original one. So 34 minus 52. And the original deviation was 12. Okay? So the reason why we're figuring out the z-score is because it tells us that it left the z-score unchanged. So the z-score for the original marks is going to be the same as the z-score for the new one. So we'll call this one original, and then we'll eventually do the new one. So 34 minus 52 divided by 12 gives us a z-score of negative 1.50. Okay? So now, once again, like I said, because it says the z-scores are unchanged, that means this z-score will be the same for this z-score. So I write out my formula. My z-scores are the same, so I'm going to plug that in. All right. Now my x, okay, what would be the new mark? If this is the original mark, then the new mark, that's going to be what we're looking for. Okay? So x new is what we're looking for. Now it said that my new mean, my mu new, is 65, and my new sigma is 10. Okay? So when you rearrange to solve for x, okay, so the first thing we're going to do is multiply by 10. So that's going to give us negative 15, and then x minus 65. And then I'm going to add that 65. So I'm just doing algebra here. So negative 15 plus 65 gives you 50%. So that is the student's new mark. Yay, we did it! Okay? So overall, this lesson, although it was a long one, okay, we practiced using this formula. So you definitely need to know how to solve for any of these values in this formula, okay? So that was the one big idea. And then the second big idea was this bad boy here, this bell curve. Okay, so make sure you know how to use both of those things. Okay, you're looking at the 20-2. So Z-scores, we're going to talk more about Z-score tables on Monday. And then your guys' quiz is on Tuesday. So Monday's a double day. So we're going to get through that lesson. Okay, which is it's another, actually it's not that bad. It's only 2.5 pages. So for homework, okay, there are 12 questions. I would expect that you would get through at least half of them this weekend, so that on Monday we'll do the lesson, and then it gives you time to study in the second block. Okay? All right, you guys have a great weekend, and I'll see you Monday.